Consider this. When you stick a straw in a glass of water, it looks bent, right? That's because light bends or refracts when it moves from one material to another, like from air to water. For centuries, we thought light always bent the same way. We called this positive refraction. But what if we could make a material that bends light in a totally different direction, backwards? It sounds like science fiction, but it's real science, and it's happening today. These incredible materials are called metamaterials, and they are unlocking a whole new world of possibilities by controlling light in ways we never thought possible. So, what does it mean to bend light backwards? Imagine drawing a line straight down on a piece of paper. That line is the normal. When light hits a surface, like water, it bends away from that normal line at a certain angle. This is what we see every day. Negative refraction is when the light bends on the other side of that normal line. It's like the light is being pushed in the opposite direction you'd expect. To make this happen, a material needs something called a negative refractive index. It's a number that tells us how much and in which direction light will bend, and for these special materials, that number is less than 0. This isn't just a weird party trick for light, it's a fundamental shift in how we can manipulate the world around us. Think about it. If we can control the path of light with this much precision, we can create things like super lenses that can see things smaller than the wavelength of light itself. That could revolutionize medicine and electronics. We could also, theoretically, create invisibility cloaks. By bending light waves around an object, it would be as if the object wasn't even there. The light would just continue on its path, leaving the object completely hidden from view. The magic behind these metamaterials isn't in the stuff they're made of, but in how they're built. We're not using some exotic element from another planet. We're using common materials like gold, silver, and silicon. The secret is to structure them at a scale smaller than the wavelength of light itself. By creating tiny, repeating patterns, we can trick light into behaving in these extraordinary new ways. These structures interact with the light waves, guiding them along paths that nature never intended. It's a bit like building a custom-designed obstacle course for light, forcing it to take the exact route we want it to. To understand how this works, let's zoom in on one of the key building blocks, a plasmonic waveguide. Imagine a super thin sandwich. The bread is made of metal, like gold or silver, and the filling is a non-conducting material, or dielectric, like a thin layer of silicon nitride. This is called a metal-dielectric-metal, or MDM, structure. When light hits this tiny sandwich, it doesn't just pass through. Instead, it gets the electrons in the metal to start jiggling in a very specific, collective way. This energetic dance of electrons, coupled with the light, is called a surface plasmon polariton, or SPP for short. These SPPs are the key to everything. They are waves that are trapped, zipping along the surface between the metal and the dielectric. Think of them as light that's been squeezed into a tiny, flat tunnel. Because they are confined in this waveguide, we can control how they move. The shape and, most importantly, the thickness of that dielectric filling determine everything. By carefully engineering these tiny dimensions, we can change how the SPPs behave, giving us incredible control over the properties of the light that created them in the first place. Now, these SPPs can travel in a couple of different ways, or modes. One is the symmetric mode. In this mode, the electron waves on the top and bottom metal layers wiggle in sync, like two people doing the wave at a stadium perfectly together. This mode behaves normally, it has a positive refractive index. But there's another mode, the anti-symmetric mode. Here, the electron waves on the top and bottom are out of sync. When one zigs, the other zags. This opposition creates a backward flow of energy. It's this anti-symmetric mode that produces the amazing effect of a negative refractive index. So, how do we pick which mode we get? It all comes down to the light we use. Let's say we build these tiny waveguides with gold or silver on a silicon nitride membrane. If we shine red light, which has a longer wavelength on them, we might excite the symmetric SPP mode, and the light bends normally. But if we switch to blue or violet light, with a shorter wavelength, we can hit the sweet spot that excites the anti-symmetric mode. When that happens, presto! The angle of refraction flips, and the light starts bending backwards. We can literally change the color of the light to turn negative refraction on and off. Having one tiny waveguide that can bend light backwards is cool, but it's not a full-fledged material. To make something that you can actually hold and use, we need to think in 3 dimensions. The next brilliant step engineers took was to stack these little metal-dielectric-metal sandwiches on top of each other, one after another. Imagine making a huge stack of pancakes, but where each pancake is one of these plasmonic waveguides. This creates a bulk metamaterial, a 3-dimensional structure that can manipulate light passing through it in a consistent and predictable way. By stacking these layers, we create a material where the negative refraction effect isn't just a surface phenomenon, it's a property of the entire volume. When a beam of light enters this stacked structure, it interacts with layer after layer of these waveguides. Each layer contributes to the overall effect, guiding the light along a negative path. The result is a solid material that, to the naked eye, might just look like a small chip, but it has the incredible ability to bend an entire beam of light backwards. This was a huge leap forward. The most exciting part is that this stacking method works for visible light. For a long time, creating negative index materials was only possible for longer wavelengths, like microwaves. But by using these plasmonic waveguide designs with materials like gold and silver, scientists have successfully built metamaterials that exhibit negative refraction for the very colors we can see. This brings all those science fiction ideas, like superlenses and cloaking devices, one giant step closer to reality, because they need to work with the light we use to see the world. This isn't the only way to build these amazing materials either. Scientists are always experimenting with new shapes and structures to achieve this effect. One very promising design is the coaxial waveguide. Think of a tiny, tiny coaxial cable, the kind you might use for your TV, but shrunk down to the nanoscale. It has a metal core, a dielectric insulator around it, and a metal shell on the outside. This structure also supports modes that lead to a negative refractive index, and it works for a wide range of colors and angles, making it very versatile. It's all about finding the right geometry to make light do our bidding. Another clever design that shows this amazing property is the core shell nanoparticle. Imagine a microscopic ball, or core, made of one material, wrapped in a shell of another. For example, a dielectric core could be coated with a plasmonic metal shell. When light hits these tiny coated spheres, they can resonate in a way that produces both a negative electric and a negative magnetic response at the same time. This is the perfect recipe for creating a negative refractive index. By mixing these nanoparticles into a solution or a solid, we can create a metamaterial that's easy to produce. What makes these nanoparticle and coaxial designs so powerful is their robustness. They often work over a broad spectrum of colors and from many different angles of incoming light. This is a huge advantage over the early metamaterial designs, which were often very picky. They might only work for one specific color coming from one specific direction. Having materials that are more flexible and forgiving makes them much more practical for real-world applications. It means we don't need perfectly controlled lab conditions for the magic to happen. So, why does any of this matter? Unlocking the ability to control light with negative refraction is more than just a scientific curiosity. It's a gateway to transformative technologies. Think of medical imaging that can see individual viruses inside a living cell, or optical computers that use light instead of electricity to process information at incredible speeds. It could lead to more efficient solar panels that trap and guide sunlight, or communication systems that can send more data through smaller fibers. We're just scratching the surface of what's possible. The journey into the world of negative refraction is a perfect example of how science works. We started with a fundamental question: can light bend backwards? By combining our understanding of physics with clever engineering at the nanoscale, we found that the answer is a resounding yes. From simple waveguides to complex 3-dimensional structures and nanoparticles, we are learning to write new rules for how light behaves. These discoveries are paving the way for a future where we can manipulate light as easily as we manipulate electricity today, leading to technologies that will change our world. Consider that. Consider